Welcome back, statistics people. Today we're going to start our look at the binomial distribution, and to do that we're going to start by looking at a game of basketball. In fact, we're going to look at one very particular basketball game. The 2005 Conference USA basketball tournament, Memphis trailed Louisville by 2 points, and at the buzzer, Memphis's Darius Washington attempted a three-pointer. Now, he missed a three-pointer, but he was fouled in the act of shooting. So he went to the free throw line to shoot 3 free throws. Each free throw is going to be worth 1 point. So was it a smart idea to foul? Of course, this kind of presumes that you have some idea about basketball. But what are all the different ways that this could have happened? Well, the first one would have been 3 made free throw points. And I've done a tree diagram here so we can see it. So the first one he makes, the second one he makes, the third one he makes. Okay, that's one thing that could have happened. Another thing that could have happened is he could have made the first 2 free throws and then missed the third free throw. So that's a make, and then a miss. Okay. Another thing that could happen is he could have made the first free throw, missed the second free throw, and then made the third free throw. So that's a made free throw, a missed free throw, and then another made free throw. And then on the same branch, we would have a make, miss, and a miss. So a make free throw, and then 2 misses. Okay, so I think that it takes care of everything that could happen if he made the first free throw. But what if he missed the first free throw? Well, if he missed the first free throw, we can go down this path, and you can see he's going to miss the first one, and he's going to make the next 2. Alternatively, he can go down this path where he makes the first free throw. He misses the first free throw. He makes the second free throw, but he misses the very last free throw. Two more options, and in this first option, he misses the first free throw, he misses the second free throw, but he makes the very last free throw. And in this very last option, he misses all 3 free throws. So Darius Washington was a 72% free throw shooter. Find the probability that Memphis wins, loses, or goes to overtime. And when you've found the probabilities, put them in table 3. Well, since I already have a tree diagram here, we can go ahead and compute the probabilities this way. Now, this first one is if he made all 3 free throws, that's 72% multiplied by 72% multiplied by another 72%, and that gives us a probability of 3732. The next possibility is if he makes the first 2 free throws, makes, and then he misses the last free throw. So that's 0.72 squared multiplied by 0.28 to the first power, really. That's 1451. Next, we could make, miss, and then make, and that would give us 2 made free throws at 72% and 1 missed free throw at 0.28%, and that's 0.1451 again. So as you can see, they're all kind of done here, and let's highlight Memphis winning the game, and that's this one right here. That's the only way that they make 3 points to win the game. Back over on our master chart, we can see that that probability is 0.72 cubed, which is 3732. Now let's take a look at all the different ways that they're going to lose the game. So they're going to lose the game if he only makes 1 free throw or if he misses all of the free throws. So let's see, which ones are losing the game? That's this one right here, and this one right here, and this one right here. And then we're going to treat this one just a little bit differently. So you will notice that we have 3 opportunities, or 3 of those losing opportunities are 0.72 to the first power multiplied by 0.28 squared. And one of them is 0.28 to the third power. Back to my master chart, and that means that we have 3 times 0.72 multiplied by 0.28 squared plus 0.28 cubed, which is 0.1913. And now let's talk about overtime. They're going to go to overtime if only 2 points are made by Darius. So here we got 2 points, 2 points, and 2 points. You'll notice that all the calculations are the same. It's 0.72 squared multiplied by 0.28 to the first power, giving us 0.1415. And we'll just put that number in our chart over there. So what have we learned from this? Well, we have learned that if the probability of making that free throw is the same, which is to say that it's independent, at this point, Memphis has a 37% chance of winning, only a 19% chance of losing, and about 44% chance of going to overtime. So in all likelihood, looking at what we see here, in all likelihood, they're going to either win or go to overtime. There's a 20% chance to lose, but that's a minority chance. So let's take a look at what happens here. Prior to watching each shot, calculate the probability that Memphis is going to win the game or loses the game. Okay, so right now there's 3 shots remaining. We have those probabilities, so let's write them in. Now you can go ahead and Google this game. I believe it's online. It's on YouTube. I know I watch it on YouTube just about every year thanks to teaching stats. But what happens after is that he makes the first shot. So he makes the first shot, so the game is now 75-74. Feeling pretty good. He's got 2 shots remaining. So the probability that Memphis is going to win, well, that's going to be 0.72 squared, because he's got to make the remaining 2 shots in order for Memphis to win. And the only way that they're going to lose at this point is if he misses both shots. So that's 0.28 squared. So that's about an 8% probability that Memphis is going to lose at this point. And then the probability that they'll go into overtime was if he only makes 1 of the shots. So he could make the first shot and miss the second shot, or he can miss the first shot and make the second shot. That gives us a probability of 0.4032 that they're going to go to overtime. Again, if you watch the game, you will know that he's going to miss the second shot, so the score is going to remain 74-75. Now, there is no chance that they're going to win. If he makes the shot, they'll go to overtime. But if he misses the shot, they're going to lose the game, so 0.28. Okay, and what happens? Well, actually, poor Darius misses a shot, and Memphis loses the game. I watch this every time, and every year, it's a crushing performance, and you feel really bad for Darius here, but that's the way sports go, I imagine. So they lose the game. So right at the beginning, they were a part of this about 20%, 19% chance of losing the game. So Darius Washington is a 40% free throw shooter. Do you think it was smart to foul? Well, let's see. Darius had to win the game, he had to make that free throw point shooting. So to win the game, let's say they don't foul. the probability of winning the game was 40%. And the probability of losing the game was 60%. And the probability of overtime was 0%. If they did foul, the probability of Memphis winning dropped to 0.3732. The probability of Memphis losing also dropped to 0.1913. And then the probability of going to overtime jumped up to 0.4355. So if you're Louisville here, should you foul or should you not foul? And let's see, if you're Louisville and you see these numbers, it looks like Louisville had a better chance of winning if you don't foul them. So the chance of winning without fouling is 0.4, and the chance of Memphis winning if you don't foul is 0.4, and the chance of Memphis winning if you do foul is 0.37. So actually, if you look at it in terms of that, the probability of, let's say Louisville, your team, if the probability of Louisville losing if you don't foul is 0.4, and the probability of Louisville losing if you do foul is 0.37. So there's an argument to be made here that it was actually a good idea that they would have fouled him. Kind of goes against conventional wisdom. If you listen to basketball commentators, they'll probably say not to foul the 3-point. But statistically speaking, it looks like it would have been better to foul. Okay, so let's move on, finish here to our important ideas. And what we just did was something called a binomial experiment, or a binomial setting. Now, a binomial setting has 4 components to it, or there are 4 things to qualify an experiment into a binomial experiment. Number 1, the outcomes need to be binary. That means that there's only 2 outcomes that could happen, either win or lose, make or miss. Each of the outcomes have to be independent, so we had to buy into the fact that Darius's first shot isn't going to affect his second shot. That may or may not be true, but in order for this to be a binomial setting, we would have to assume that that's true. And it's not a big deal because there are plenty of places where this is definitely true. There has to be a set number of trials. In other words, with this experiment, Darius only shot 3, and he had to shoot 3. Well, I guess technically he didn't have to shoot 3 if he missed the first 2. But there are 3 shots to be made, no more, no less. And lastly, the probability has to remain the same. So the probability of success has to be always the same. For Darius, that's the 0.72 free throw shooting. If you can believe all of those are true, then what you have created is a binomial setting. And to compute the binomial setting, we're going to do the total, we're going to do this calculation right here, NCK, where N is a total number of shots or trials. K is the number of successes that we're interested in. So this says the probability that we have, let's say 5 successes would be NC5. P is the probability of success. So this kind of makes sense. If we're interested in, say, 5 successes, then we're going to say the probability of success to the 5th power. And if we have 5 successes, then the remaining of the successes need to be, or the remaining number of trials need to be failures. So they have to be failures. These 2 numbers here, they have to add up to N. So that's a real quick kind of a way to make sure that you did this correctly. So probability to the K, probability of success to the K power, probability of failure to the N minus K power, and then there's this NCK business. So the formula for NCK, that is K factorial over n factorial multiplied by n minus k factorial. It's a pretty commonly used calculation. Most people would call this n choose k. So for example, slight problem with that formula. The numerator should have been n factorial. So n choose k is n factorial over k factorial multiplied by n minus k factorial. So if we have 3 choose 2, that's 3 factorial over 2 factorial multiplied by 1 factorial. And that gives us 3. If you remember from Darius, we had that 3 choose 2 here, 3, 0.72 to the first power, 0.28 squared. So that 3 right here, that was 3 choose 2. And this 3 over here, this should have been 3 choose 1. In any case, none of that's going to matter because your calculator will be calculating all of your combinations for you. So you just need to write down that combination, say that you're going to do it on your calculator, and then just do it on your calculator. So we'll get into how to do that on your calculator in 1 second. So in your check your understanding, we've got for each of the following situations, determine whether or not the given random variable has a binomial distribution, and then justify your answer. So this first one, shuffle a deck of cards, turn over the first card, put the card back in the deck and shuffle again. Repeat this process 10 times. Let X be the number of aces you observe. So first of all, is this binary? The answer is yes. It's ace or not an ace. Is this independent? Okay, well, if the probability of getting an ace doesn't affect the probability that of the next card being an ace, then yes, probabilities do not change. Probabilities do not affect, I should say current probabilities do not affect future probabilities. Is there a set number of trials, n? And yeah, we're doing this 10 times. No more, no less. And finally, do we have the same probability of success? Yes, it is. P is 4 ace cards out of the 52 in the deck. So this is, yes, binomial. Let's take a look at B. Choose 5 students at random from your class and let Y be the number who are over 6 feet tall. Are these binary outcomes? And yes, it is. Either the students or, well, hold on. Yeah, either the students are above 6 feet or they're not. Independent. If I choose one 6-footer, is that going to affect the probability that the next student is going to be a 6 foot? Oh, that is going to change. So no. Choosing a student that's over 6 feet tall is going to mean that you have one less student who is 6 feet tall to choose from. So the probability that the next person is 6 feet tall is going to be decreased. So this is not independent. This kind of goes hand in hand also with S. So let's just go through the rest of this. Is this a set number of trials? Yeah, we're doing this 5 times, but is it the same probabilities? And no. The probability is different. Probability is different for every student, depending on how many students are picked. So this is not a binomial situation, okay? 2. Pedro drives the same route to work on Monday through Friday, and his route includes 1 traffic light. According to traffic department, there is a 55% chance that the light will be red on a randomly selected workday. Suppose we choose 10 random work days and let Y be equal to the number of times that the light is red. So let's go with this. Is this binary? Yes, it's binary. Either the light is red or the light is not red. Are the lights independent? Yes, the probability that the light is red on one day should not affect the probability that the light is red on future days. Do we have a set number of trials? Yes, there are 10 days that we're going to be computing this for. And finally, do we have the same probability of success every time? And yes, we're told that that probability that we get a red light is 0.55. So letter B is we're going to find the probability that the light is red on exactly 7 days. Notation-wise, we want to say the probability P that the number of red lights is equal to 7. The next thing you're writing here is 10 choose 7. So always the bigger number first, 10 choose 7. Then we write the probability of success, 0.55, to the appropriate power. And this power for the probability of success always matches the second number on the combination, on the 10C7. And then the last thing we write is the probability of failure, which is 0.45, 1 minus 0.55, to the third power. Now to get that 3, you just got to know that the two powers added together have to add up to n. So you can do a subtraction if you want, or you can just, however you want to compute that. That's going to be 0.45 to the third power. Now you grab your calculator. On your calculator, you're going to go to Math, Probability, and look, there's NCR right there for number 3. I know that in most stats class we say NCK, but NCR is really the same thing. So let's go to NCR, and you'll notice that there are 2 blanks that we need to fill in. Naturally, we're going to fill them in with 10 and 7. Scroll to the right here, and we're going to put 0.55 to the 7th power, multiplied by 0.45 to the 3rd power. And that gives us our result, 0.1664. See, I told you you don't have to worry about that formula. Your calculator is going to take care of that for you. So there we go. There's how we're going to calculate our binomial distributions. This is a pretty big topic, and we don't really have a whole lot of time to go through it, unfortunately. This is going to feel really brief, or it feels really brief to me. So hopefully we can get you more practice as we go on in class. So that's it for today. See you next time here at AP Stats.